So total internal reflection occurs only when light is traveling from a more dense medium to a less dense medium. And we can calculate that critical angle, and it depends on the indices of refraction for both media through which the light is traveling. So we take N1 to be the index of refraction for the more dense medium, and we take N2 to be the, because we're traveling from 1 to 2, take that to be the index of refraction for the less dense medium. So the sine of the critical angle is just equal to the ratio of the two indices. So N2 divided by N1. Okay, so sine theta equals N2 over N1. If we rearrange that, right, anytime we want to find an angle, we have to use the inverse of the trig function. So in this case, it's sine. So it's just going to be the inverse sine of N2 over N1. So here what we're going to do, we're going to calculate the critical angle for total internal reflection. The light's going from diamond to air. Notice for air I rounded it to 1.0003. And the index of refraction for diamond is 2.419. Okay, so we've got our two indices. We know it's going from diamond to air. So this will be our N1, and this will be our N2. So we know the sine of the critical angle equals N2 over N1, where this is the index of refraction for the less dense medium over the index of refraction for the more dense medium. That's the only way sine will work, right? Because the sine of any angle is between -1 and 1. Okay, so then just rearranging, right? We got theta equals the sine inverse of N2 over N1, and now we'll plug in our two indices of refraction, and it's always going to be the smaller over the greater. And when we do that, we get a critical angle of 24.4 degrees. So for any incident angle greater than 24.4 degrees, the light passing through the diamond will be reflected back into the diamond. That's why diamonds are so nice and shiny, right? Because they've got such a small critical angle. You don't have a lot of light escaping from them.